Grace and Caitlin, because they park. I always leave.
Oh, you know what I can do? It's a little dangerous.
There's one time we went to breakfast together and she got school and she just laughing. I don't know what I'm going to do this year. That's my own conversation. Like, he may be great at everything else in the world.
All right. So, exponentials and logarithms. Do you remember how to do all of those? Yep. I hope so. Okay, let's talk about exponentials first. Raising things to a power. I know you know it all, but let's just be sure and do some double checking. So, if you have two things that have the same base, and they're multiplied, you get 10 points for Ethan. Yes. What if you have two things with the same base divided? All right, Andrea. There you go.
Yes.
All right. What if you have x to the a raised to the b? Wow. Awesome.
Yes.
Let's do one more. What's x to the minus a? Geniuses. Okay. What if you have this? X to the a over b. Oh, I'm messing it all up. Ethan's saying it correctly, but I can't do it. The bth root of x to the a. Yeah, duh, right? Just the bth root to the x to the a. Okay, got it, thanks. So, you should be comfortable with doing these kinds of things with just ordinary numbers. So, I mean, like let's take, like if you had 9 to the 3 halves, that should not scare you, right? You're not scared? Parker's not scared? Parker, tell me how to do this.
You just take the square root of 9, which is 3, and then you get the cube root of 3, which is 27.
Perfect, right? See, that was easy. No one's upset. We're all calm and collected. Yeah, this is too much. Okay, good. And you can have multiple things going on. You can have like 4a squared b to the 8 c to the, let's say, 4/3. And you're okay with simplifying stuff like that. That's not a big deal, right? Right. Abby, how would you start simplifying that?
You have to keep a underneath because it's 2.
Mm.
And then you move the b outside. You have a b squared.
You have a b squared, and the c?
And the c would be
One-third. Uh-huh. Let's talk about the a. You said keep the a under. So if you want to do that, I would just need to leave it as a square root and not as a 4th root. Because it'd be a to the 1/2 or a to the a square root. Or you could say it like this. You could say a to the 1/2, b2, c 1/3. Yes, Mary Elizabeth?
Oh, that was my question.
Aha.
Can you do 1/2?
Yes, you can. Okay. Any issues with that? Yes. Great. Okay. So those are basic exponential rules. Really helpful, really good to know. And then let's talk about the logarithm rules. So let's just say we have log x plus log y. That is Caitlin? Log x plus log y, simplify. Yes, log xy. Okay. What do we think? What would you do with that? Parker?
Is it log x plus y?
No. Can't do anything with that. I tried to trick you. I succeeded. It's like, this doesn't seem right. There's no special property for multiplying a log of something times a log of something. It's true that if you have a log of a product, right, you could have a b squared, for example, and you can separate that to log a plus log b squared. Then what could you do with the log b squared? 2 log b. So log a plus 2 log b. Okay, so just trying to keep it straight for you. Right, so if you have 2 logs added together that have the same base, you can multiply the insides. Let's see, what if I have this? Right. Divide the insides. What if we have something like this? Okay. 3 to the log base 3 of x cubed. Let's go with Jack. Do you remember how to do that?
Is that just... I can't read the top of it.
Oh, sorry. It is. Oh, watch this.
Can the 3's just cancel out?
Which 3's?
The log 3x3 and the big 3 and it become log x cubed.
Close, but not quite. Kathy?
So it's, you just, the log and this 3 cancels out, so it's just x, right?
It's just x to the third. Right, that's what it ends up being. Oh no. Y. 3 to the log base 3 of x cubed. So you got to recall, first of all, what does it mean to take the logarithm of something? Right? What does this mean? Log 3 of x cubed. We're asking the question, 3 raised to what power gives you x cubed? Right? So it's saying this is the exponent you raise 3 to get x cubed. So it's an exponent. And then you take 3 to that exponent. You get x cubed. Right? So, but then the other way to think about it is just the definition of a logarithm, which is, let's see if I can write it out. So if you have x to the a equals b, that's the exponential form of a number. And the logarithmic form of a number. So if you raise x to the a power, you get b. That's the logarithmic form. What power do you raise x to get b? A. So remember this is, and so I can go back and forth, right? Do the pool ball thing. B equals x to the a. These are all showing the same kind of relationship. It's just a different way, right? Exponentials and logarithms are inverses of each other. What do you think? Kind of difficult. Okay. Hey, can you spotlight where the hard part is?
Just like,
Remembering it? Well, let's think of an easy number, right? Could you think of how 10 to the 2 equals 100? So can you understand that log of 100 is 2? See how the logarithmic exponential form are just...
Wait, this is just the
It's just a pool ball thing. It's just a pool ball thing. That's all. Okay. You see what I'm saying? It's just one way to write it is 10 to the 2 equals 100. The other way to write it, so 10 to the second power equals 100. Then you say log 100. What power do you raise 10 to get 100? 2. So it's just different sides of the same coin. What's that, Ian? Oh, really? Okay, good. Glad to hear it. Okay. Goodness, what is going on? Sorry, I was worried there's some kind of emergency. I was getting like several text messages. Okay. Everything's okay. Okay, so we have that. So what if we have this? ln e to the pi power. Kathy?
It's just pi.
It's just pi. So just remember they're inverse operations, right? The logarithm and the exponential. So if you take the log of an exponential, you get whatever the input to the exponential was.
What about e to the ln?
Yep. Okay. Any general questions about those rules, operations? So we have sum of logs to being a log of a product, difference of logs being a log of a quotient. We have log of a number to a power. Let's say log 5. No, let's make it general. Log A. No, I like B better. Log B of A to the x does equal x log B of A. So that ability to shift the exponent down to the front. Okay, so those are just some of the general properties. Mary Elizabeth?
Are like the two above it with the natural logs like the same version of themselves? Like how do you get from the first one to the second one? Or are they just like two different ways to write pi?
Oh, yeah. So, so these are different steps. So this is, the one on the left is you do e to the pi, and you take the natural log of it, you get pi. The other one is you take natural log of pi, you exponentiate it, you get pi. It's showing that they're inverses. Doesn't matter what the order is in which you do them, you still get the same, excuse me, same final answer. Did that answer your question?
Yeah.
I'm a little worried I didn't. Okay. I think there are plenty of good practice problems. Be sure to also make sure you use your old tests to study for this. This can be really helpful to go through those. Okay. So then the graphs. The graphs. Easy part, right? You know the general shape, right?
That one.
That's that way. So is there a horizontal or a vertical asymptote? Horizontal. Yes, it looks like this. And there's the asymptote at y equals 0. What about e to the negative x? Flip it which way? Yes, horizontally. Reflection about the y-axis. What about y equals negative e to the x? I know what you mean. And then what about, finally, negative e to the negative x? But you can do it.
Just flip that one and that on the bottom. The opposite time. On the negative side, it seems like they're on.
something like that. So just simple transformations, you know. Putting a negative in front of the whole function flips it vertically. Putting a negative in the argument flips it horizontally. Let's see. Well, let's see. Do we know? So if we have a function which is ln x, let's go. Mia, do you know what it looks like? Yep. So there's a vertical asymptote. Good. So there's a vertical asymptote at x equals 0, and the function goes like this. So it's the interesting thing to keep in mind about natural logs. What's the domain of a natural log? Let's go, Ethan. Domain of a natural log.
From 0 to infinity.
0 to infinity. So in other words, you can't put negatives inside the natural log. But what's the range of the natural log? All real numbers. So it can be negative. You can get negative outputs for logarithms. Right? If you take a simple example, right? If you take, I'll just do it up here. If you take log base 2 of 1/2, you get -1. Right, because that's just log base 2 of 2 to the -1. -1. You can get negatives on the output, but you can't put negatives on the input. Okay, so that's a natural log graph. But we can imagine doing things like this. So let's just look at a few. We can imagine doing negative ln x. So let's go with Mary Elizabeth. How would that make the graph look?
Would it go the other way with like a vertical asymptote, or would it go upside down?
Upside down.
All right, so it would go like go outwards as you get there.
That. Yes. So it would go like.
Oh wait, because you can't have negatives. Just remember that.
Can't have negatives on the input,
Yeah.
but you can flip all the outputs. So it takes that kind of direction. Okay. What if I did something like this? What if I did g of x equals ln negative x? Ooh. Caitlin, do you know ln of negative x? No? That's fine. Abby, do you know? This way? No? That's kind of like this one goes that way. Flips down. Andrea, do you know what happened if I had to put the negative in the argument? Yes, and Abby got it too. So you both put it together. Good. So it would go like that. Right? Because then if you ever put any positive numbers in for x, like if you plugged in, let's say 1, it would be ln of -1, which is undefined. But if you put in -1, ln -1, which is ln 1. It is defined. So it flips it all horizontally. Okay? And then one of the ones we looked at was this interesting function. Oops. We looked at ln absolute value x. What's that, Elizabeth? Yeah. Yeah, you're right. It goes like that and that. And let's think about why that is. If you put in positive numbers, then it's still just like ln x, right? It's still just like, absolute value won't do anything. Just makes whatever number you put in, well, it's positive, so the number you put in is still positive. you put in negative numbers, though, it makes the negative numbers positive, so it does the same thing. So is that you're building the graph on the right side. If you put in 1, absolute value, if you put a negative 1, it makes it absolute value, so 1, and so it will do the same thing on the left side as you build up. And now that you've seen all the piecewise functions, you can think of that, f of x equals ln absolute value x, as just a piecewise function, ln x when x is greater than 0, and ln negative x when x is less than 0. So 2 pieces. Negative ln negative x. So we would simply take this graph right here, the ln negative x, and flip it vertically. So y equals negative ln negative x would be just that. Okay. Any big questions about all of this? Little questions about all of this? Keep moving on. Yes, Parker.
How many tests did you take?
One on conic sections, one on polynomials, one on exponentials logs, one on discontinuous functions, and then the last one on limits and sequences and series. So 5 total for the whole semester. Yep. You learned a lot. Pretty sweet. You're welcome. Okay. Ready for discontinuous functions? Okay. So, what was the most basic discontinuous function we looked at? Anyone know? 1 over x. That is such a common function. You should always know how that looks. Do not go into calculus next year not knowing how that looks. Most basic discontinuous function that we looked at was that one. So it's got vertical asymptotes and horizontal asymptotes. But in general, so we looked especially at rational functions, then we looked at piecewise functions. For a rational function, we need to know of several things to be able to graph it and analyze it. Right, Ian? What are some of the things you need to know to graph a rational function? What's that called? A hole? Okay, so holes. We need to know where holes are. How do you figure out where a hole is in a rational function? Kathy?
So if you factor the function and it has like the same thing.
Yes.
Like on the
Yes, common factor, numerator and denominator. Cancel it out. You know there's a hole at the root corresponding to that factor. Okay, what else, Caitlin, do you need to know for graphing rational functions? Very good. And how do you know where the vertical asymptotes are? Don't remember? Okay, we're going to dig it up. Abby? The factor at the bottom and then do what with it? Yep. So set denom equal to 0. Okay. Parker, what about horizontal asymptotes?
Horizontal asymptote is, they have the same leading coefficient term. You just put the numerator over the denominator for leading coefficients. And if the denominator is bigger than the numerator.
All right. Yeah, let me start.
And the numerator is going to be the denominator. You divide the numerator by the denominator by the same.
Okay, so if the denominator has bigger than degree than the numerator, it's just y equals 0. The first thing you were saying is if they were equal. Yes. So that's the ratio of leading coefficients. And then what was the last one you said, Parker?
If the denominator was less than the numerator, then it doesn't exist.
Yep. Yes. Yes, Kathy.
What is the in parentheses after the y equals a?
Ratio of LC, meaning
Oh.
leading coefficients.
Okay, so I can't read it.
That's okay. Probably my fault. All right. Anything fuzzy about that? Are you okay with that? Kathy?
I forgot how to do this.
How do you do slant asymptote? Well, let's look at a simple function, see if we can figure it out. So you just need a function that has a higher numerator than the denominator. So let's see if we had something like okay, let's say we had that. So divide the numerator by the denominator. So you will most likely need to do long division. So numerator 4x cubed. Don't forget placeholders. So like a 0x squared minus 3x plus 1. And then you're dividing by 2x squared plus x plus 0. Okay, so then you would just do that long division. So this goes in 2x times. So that gives you 4x cubed plus 2x squared plus 0. You subtract negative 2x squared minus 3x plus 1. Then that goes in minus 1 times, so you get minus 2x squared minus x and if you had to keep, that's your remainder here, so your slant asymptote would just be y equals 2x minus 1. Like that. It's just that linear term that comes out.
So don't worry about whatever that comes out.
Don't worry about the remainder.
You can still have a vertical asymptote.
Right. Because it gets at, you got to remember, what are these asymptotes telling us? The vertical asymptote is telling us, okay, at one particular value of x, the denominator is going to 0, which means the whole thing goes to infinity. Right? Like 3 over 0, if you're getting closer and closer to 0, the whole thing's going either to positive infinity or negative infinity, depending on the signs involved. But for the horizontal asymptotes, you're asking the question, what happens when x gets really, really big? When x is really huge, what does the whole function do? That's why if the numerator has a bigger degree, the denominator has a bigger degree, well then the denominator gets massive. So you have some number divided by a huge number, which goes to 0. Yeah?
And you can't cross vertical asymptote.
That's correct.
And you
Right.
can't cross horizontal.
You can cross horizontal. Right, because again, horizontal is all it's telling us is the details from far to the left and right. But the vertical is telling us the details at one particular value of x. So you never can cross it because it's telling you that the function blows up at that value. Can't do it. But at far from the ends, that's just saying far away that's got to go to 0 or 1 or whatever. So in the middle, you can cross it if you need to, or if the function demands it. Okay, so we have the asymptotes, the holes. What else do we need to know? X and Y intercepts. Yes, thanks. So the intercepts, and Andrea, how do you get the X intercepts? Yeah. Yeah, that's right. Because really you're saying when does the whole function equal 0? And a fraction equals 0 when the numerator equals 0. So therefore you just set the numerator equals 0. Y-intercepts. Yes. So you set x equals 0. Right, because that's saying, okay, when x is 0, so when you're on the y-axis, where does the function hit? So, I mean, those are the basic ideas behind the rational functions. If you can just find those pieces, horizontal, vertical, slant asymptotes, x, y intercepts, if you can just find those pieces, then you should be able to graph it. Now it's true, sometimes you have to really think about it, like you might even have to plug in values or do the analysis to say, is it going to go up here or down here? Is it above the axis or below it? But that's the general pieces that you need.
To do the above or below, we do the number less than the asymptote, right? So lesser or greater.
Right, so I mean, let's look at one of the ones from one of those tests that we took. This was on an old test, y equals 1 over x squared. We can click, it's not hard to figure out the asymptotes. You see vertical asymptote, x equals 0, horizontal, y equals 0, no intercepts. So you can quickly get a graph together that looks like, okay, asymptotes on the axes. Now where do I draw it? So you know at x equals 0, it's going to be blowing up. It's going to go to infinity or negative infinity. So you ask yourself the question, as x goes to 0 from the right, what's happening? So you plug in something a little bit bigger than 0. So that'll give you 1 over a positive squared, which is a positive. So that means the limit as x goes to 0 from the right of this function y is infinity. Do the same thing as x goes to 0 from the left. 1 over a negative squared is also a positive. So the limit of the function as x goes to 0 from the left is still infinity. And so that actually in itself is enough to tell you that it needs to look like that. Okay? All right. So I want to just hit a couple specific things. So that's the general overview of rational functions right there. Just a couple specific things. If you look at your final exam review, number 3. Number three. Okay, determine if the following equations are for an ellipse, circle, hyperbola, or parabola using the shortcut method. So let me tell you about this shortcut method. It's really nice. I think you can see it. So let's look at the first equation. 2x squared plus 2y squared minus 4x plus 6y minus 10 equals 0. So first of all, if you want to get the exact equation, what whole process are you going to have to do to get the equation of the conic section? You need to factor it, and in this kind of way, it's a special kind of factoring which we call completing the square. So in order to really get it down, you'll have to do that. But there is a way to see the shape before you even do all that. So you just know what kind of section it is. And it involves focusing on these square terms. So look at the square terms. If they are both positive, then it's either going to be a circle or an ellipse, because circles and ellipses have both positive square terms. It's only the hyperbola that has a plus and a minus. So I guess I should say if they're the same sign, because technically you could have them both negative, but when you solved it all out, the negatives would cancel and they both become positive. So if they both have the same sign, then that tells you circle or ellipse. Then the other piece here is you got to remember that circles have the same coefficient, right? It's x squared plus y squared equals r squared, whereas ellipses do not. So if we had this equation, so x squared plus y squared equals 4, that's a circle of radius 2, centered at the origin. But if you had x squared plus 4y squared equals 4, that's an ellipse. Right? You would divide everything by 4, and you get x squared over 4 plus y squared over 1 equals 1. And this would be an ellipse stretched out along the x-axis like this. both positive square terms, but with the different coefficients it makes an ellipse. Same coefficients, circle. So then what's this equation here? Circle. Because even without doing all the completing the square, which you should do to get the final, not necessarily in this problem, but if you wanted to be able to graph it, you'd have to do that. You can see that, oh, they have the same coefficient. They're both positive square terms. Therefore, you can see that it would eventually come out to,
So because of the 2 and the 2, that's
yeah, the 2 and the 2. Whereas look at the next one, 1x squared minus 2y squared. What do you think that would be? So there's a difference of square terms.
that'd be parabola, hyperbola.
Okay, parabola or hyperbola, and Caitlin, which one do you think it is? Parabola? Okay, not quite, because a parabola only has one square term. Right, it's like y equals x squared, or x equals y squared. So it has to be then a hyperbola, where you have a difference of square terms. Yes, Andrea?
Can you complete the square for that one?
You just want to see how it's done? All right, well, let me divide everything by 2, because everything's divisible by 2, so make it easier on myself. Then you group together the like terms, so x squared minus 2x plus blank plus y squared plus 3y plus blank minus 5 equals 0. Well, I guess I can do, I'll say just equals 0. So you say, okay, x squared minus 2x plus blank. If I want to get that to be an x minus something squared, then I'm going to take the 2. Negative 2 divided by 2 is negative 1. Square it, I get 1. So I add 1 to the left. I have to add 1 to the right. Y squared plus 3y. So we got to divide the 3 by 2. 3 halves. Square it. 9/4. So this becomes x minus 1 squared plus y plus 3 halves squared equal, so then I'll add the 5 over 5 plus 1 plus 9/4. So this would come out to that. So a circle centered at 1, negative 3 halves, with a radius of root 33 over 2. Okay. Okay, and then the other thing that was sticking out to me was on the key I actually didn't write it in limit notation, but if you turn to number 9, degree and end behavior of the polynomial. This will be the last one, then I'll let y'all take off. Part B, what's the degree of the polynomial? 3. And the end behavior, so what's it doing? The ends of the polynomial. So they're going to be opposite because it's an odd degree. And since it's negative, instead of going like this, it's going to go like this. Right? So you know it's going to look something like this with the ends. And so in limit notation, we could say that means the limit of f of x as x goes to negative infinity is infinity. Right? As you go out to the left, it's infinity. As you go to the right, it's negative infinity. Just so you can see that. Well, class is over. Whoa. I'll see you next Thursday. Unless you want to come by any sooner just to chat or ask questions.